Okay, so here we go. Last time we were talking about linear approximations, and reminder, we started off with this notational convenience, which really does help us write things down without having too much bulk, and that is the magic matrix that goes right there into that position and makes this formula here the formula for the sort of general vector-valued multivariable, right? Vector value because there's several outputs, multivariable because there's several inputs, linear approximation formula. This is our most general linear approximation. Reminder why we like this formula, or why this is the right formula. It's because this is the formula that agrees with f in both value at A and all the partial derivatives at A. And very importantly, this is the partial derivatives of all of the various different output components with respect to all of the various different input components, right? And that's why the matrix has to be written exactly in this form, and be careful about, don't accidentally switcheroo the rows and the columns. It's a surprisingly easy thing to accidentally do. Okay, so another reminder, I do advise that you make this an exercise. Not necessarily in general. If you want to make this 2 input variables, 3 output variables, something like that, to keep it reasonable, then that's fine. But I do think it's a good exercise to go through and confirm that this is the right formula in general. Okay. All right, and as always, come ask me for help if you get stuck. So, plug and chug example. Here again is our formula that we're going to be plugging and chugging into. That's going to turn into this. And notice, in order to get the derivative matrix specifically evaluated where it's supposed to be at the point A, step 1 is to take the appropriate partial derivatives. Now that's various different partial derivatives. Make sure you can take those partial derivatives. Make sure you see how I'm arranging them in the particular way that I am, right? And then plugging in the point in question, right? Plugging in 1, 2. Let's see here. Why don't I make this orange? Here we go. Plugging in 1, 2 gives us our evaluated derivative matrix that then goes right there. Is that cool? Is everybody happy with that? Notice that my point where I'm doing the evaluation, you can see that right here as well. That's where that 1 and 2 came from. And all of this business right here, this is just the value of the function at our base point, our starting point, A. Okay, and again, that's just a matter of arithmetic. So all very plug and chug, but again, make sure that you follow all the little detail steps so that you can, in practice, do this, fluidly. All right. Okay. A couple of quick observations to make, while we're here. So we've previously seen, in fact, let me just scroll back up to it, that the derivative matrix, that columns, all the entries in this column are partial derivatives with respect to x1. The various different output components of f, all with respect to x1. Well, in fact, if you think about it, that means that this entire column, not the individual elements in the column, but the entire column itself is the partial derivative of the vector-valued function f. Because if you think about how would I compute partial derivatives of a vector-valued function f, well, I would take the partial derivatives one component at a time, which is what this column is supposed to be. Right? So that's just a sort of a slightly different way to think about it. You can think of specifically then of the columns. All of the columns are kind of vector-valued partial derivatives. Just a point of view. Also, let's look at the first row here. And apparently I'm taking various partials of f1. f1 being the real valued first coordinate function of f. So all of the different partial derivatives, you'll notice, x1 through xn, all of the different partial derivatives of this real valued function. Where have I heard that phrase before? All of the various partial derivatives of a real valued function. That's a gradient. That's literally, by definition, the gradient. So now it's written as a row instead of as a vector, but nevertheless, that row is the gradient of f1. And likewise, for the other rows, they're all gradients of the coordinate, component functions of f. Okay, so just kind of a nice observation about some structure that conveniently shows up in the derivative matrix. Okay, real quick, just a terminology thing. Reminder: the linear approximation is not linear. It's really unfortunate terminology, but it's this other thing called affine. You don't need to worry about what that is. It basically just means a linear function plus a constant, pretty much. Right? Anyway, so technically the linear approximation is not linear. So why do they call it linear if it's not linear? The answer is that the linear approximation, which I'm looking at here, here you go, linear approximation. I mean, other than this big constant right here, it's just a constant. It's not really doing much, right? Other than that, this part here is linear, right? So the action that this derivative matrix does, it multiplies by something, and then out comes a result that's doing most of what the linear approximation is. That, being as it is a matrix, is linear. So, anyway, that's the term. All right. Okay, so let's talk about tangent lines. I know you all know about tangent lines from single variable calculus. There is a little subtlety that I think is important, as is shows up in several places in this course. Things that you can kind of get away with being sloppy with in single variable, you can't really in multivariable. So this is one of those things. Y'all have heard me say the following before, but let's not conflate a function such as a linear approximation with the graph of the function. The graph of the function is this different thing. In this case, the graph of the linear approximation is a tangent line. Now, in Calc 1 classes, it's just kind of routine for people to, kind of refer to the tangent line as being the linear approximation, right? And to refer to the function that is the linear approximation as being the tangent line. And I mean, oh gosh, they're closely related. They're so closely related. In fact, let me change the color coding here a little bit. They're so closely related because the tangent line is the graph of the linear approximation. But again, that doesn't make them the same. That just makes them closely related to each other. Right? So heads up on the terminology. Yeah.
Why can we not say that they're the same? Like what?
Well, because they're different. They're fundamentally different kinds of critters. So this linear approximation is a function. Okay. A function is an algebraic object, right? The tangent line is not. The tangent line is a geometric thing. It's a line. It's a set of points, right? Which is just not the same thing as a function. Does that make sense? I mean, and I know it's fussy, but yeah.
Okay, all right. Then that's good. Right.
Yeah. And let me just remind you again why we have to be fussy about this and why they aren't fussy in Calc 1 classes. They're not fussy in Calc 1 classes because in Calc 1 every picture is a graph, right? And there's just no need. But now we're going to have level sets and parameterizations, and we really have to distinguish between functions and their graphs. Yeah.
Could you call the tangent line like a separate graph? Like, could you?
I don't understand. I'm sorry.
Could you define a separate graph that contains the tangent line, or is that represented by the tangent
I guess I don't quite understand. I mean, so we start with the linear approximation, right? Now we're going to set that equal to a new variable y in order to draw the graph, and that gives a very specific line that is the graph. So I'm not understanding what you mean by
like when you say that it's not equal to the graph, or that they're different things.
Yeah.
Like are they two separate graphs, or is it?
No. They're just completely different kinds of objects, right? So I like to view a function as being an algebraic object, right? And the graph is a geometric object. And again, they're connected by way of this process that, again, you form a graph by setting the function equal to a new variable. And again, this is a choice. We didn't have to do this, right? So they're different because one is constructed out of the other one. And furthermore, that construction is really not our only construction. And so, yeah, they're just very different kinds of objects. Yeah. Is that cool?
Yeah.
Okay. All right. Okay, so kind of cleaning up what y'all have seen in single variable calculus classes, and now I'm going to do the exact same thing here in a multivariable case. You see we have a function of two variables here now. The only multivariable picture I can realistically draw, right? Here is our two-dimensional linear approximation. Now dot product with the gradient, instead of just multiplying by a single variable derivative, right? So slightly different. And I can talk about its graph. And what do I get when I form the graph of this linear approximation? And if you look at this right here and think about what these linear approximations look like, I think it's a pretty easy pitch that z equals, and then this is going to be constant times x plus constant times y, plus maybe another constant, right, is going to give us a plane. And that's called the tangent plane for sort of obvious reasons, because it is just like the tangent line is tangent to the graph of the original function. The tangent plane is tangent to the graph of the original function. Okay. All right, so a little terminology there. Okay. Now a quick treatment of a deep matter. This class is not about rigorous formalities and explorations of weirdo, anomalous special cases and stuff like that. So, unfortunately, the question of differentiability is a lot harder in multivariable than it was in single variable, and it's surprising that it's a lot harder, but it really is a lot harder. I want to remind you before I go off into this, in single variable, the definition of differentiable is pretty easy. It's if you can take a derivative, then it's differentiable, right? It's differentiable if you can differentiate. It's just the same. It's like it's almost a purely grammatical distinction. And linear approximations make sense and are, what they're supposed to be when the function's differentiable. It's all kind of the same thing in single variable calculus. Not so in multivariable. Unfortunately, there's a lot to say, and it gets weird and it gets deep. So what I'm going to do is I'm just going to give us a really quick tour through some of the concerns that come up in this area. And then I'm going to write down a definition that comes out of the book, which the examples that I'm going to walk you through will kind of motivate. And then I'm going to show you how to bypass all of that for the in-practice, day in and day out, get the job done kind of stuff that this class here really is more about. Okay. All right. So let's worry now about a question that we doffed the cap to when we first started writing down linear approximations, which is this really what we think it is? You remember I asked the question, how do we know the linear approximation even exists? So, for example, let's think about this function right here. That's a weird function, granted. The value of the function is 1 when you're above the y-axis or the x-axis. So, like so. The value of the function is 0 everywhere else. Now, I'm going to represent that by kind of shading in, over here in the first quadrant. That's the function 0 all over there. And then likewise, the function is 0 all over the second quadrant. And then likewise, the third and the fourth, but the picture gets weird, so let me just leave it at that. All right? Does everybody have a clear idea of what this function looks like? The graph, that is. Okay. Well, let's take the formula that we wrote down a couple pages back, and let's write down the linear approximation. Specifically, we want to look at this point, a equals the origin. All right, well, the value of the function at the origin is 1. Right there. No problem, right? Not only is x 0, but y is 0 also. So the value of the function is 1. Nothing to it. Let's see here. What about the partial derivatives now, right? So if you're going to write down the linear approximation, we need the gradient. I claim those partial derivatives are both fine. No problem. You can see it right here in the picture. How does this function change from the origin as I move in the x direction? Well, it doesn't change at all. Starting from the origin, moving along the x-axis, the value of the function is just constant 1. Right? So that partial derivative is 0. And then now how is the function changing as I move in the direction of the y-axis? Well, again, same thing. It's not changing. The value of the function is constant 1 as I move along the y-axis. So this partial derivative is also 0, and you take all this and combine it together, and your linear approximation, with all this in mind, your linear approximation is constant 1. So let me try to draw that. All right, so okay, there we go. All right, so now what we've got here is a picture of sorts of this blue function is the original function. This green that I've drawn here is a picture of the linear approximate, the alleged, the candidate, the would-be hopeful linear approximation just from the formula we wrote down naively a couple pages back. It's this green plane right here. And I claim that is an absolutely terrible approximation for this function. Just abysmal. Let me show you how. I'm going to have to erase all of my coloring here so I can point out what's wrong with this. So let's imagine that I am approaching the origin from an angle kind of like that. Right. Okay, well, as I approach the origin like that, the function has value 0. Because I'm coming at the origin from the diagonal where neither variable is 0. That means the value of the function is 0. That means the original function is down here like that. But my linear approximation, of course, along the same path, the linear approximation's values are all 1. And so you can see there's just tremendous error here. The error is huge. The error is 1 all the way along, the whole way. That's not okay. Does that make sense to everybody? Bad linear approximation. Okay. In fact, I don't think it's reasonable to call this a linear approximation. Right? It's not doing its job. It's a terrible approximation. Yeah.
But like in single variable, like we would just chalk that up and say, oh, it's too far away from the point that we start, like our reference point.
Yeah.
Is that the same thing? Like we're starting at this crazy arbitrary XY plane.
No, I hear you, right? But in every example in single variable calculus where you have what you might reasonably call a good linear approximation, the closer you get, that error gets
Oh, it gets less. Okay.
Nice and small, right? And this is not doing that,
Okay.
right?
Yeah.
But I claim it's even worse than that. We'll get to that in a second. Yeah.
Is there any way we could patch that by like accounting for theta? Like for example, not just looking at the limits in these directions, but sort of like.
Well, so the key word here is linear, right? If you want to have something that's a nice, simple story, like just a plane, thinking geometrically, right? Then what you're describing, where the function depends on theta, that wouldn't be linear. I mean, it would be a way. I mean, I could describe the function itself that way, right? But the goal here is to find something that we would be willing to call linear in that sense of the word. Okay, so error, terrible. First thought then, my error that I'm looking at there in red, that's not approaching zero. Maybe we should require that the error approach zero. And would that be good enough, I ask rhetorically. I claim it's not. Here's why. Let's look at this function here, right, 5x. And now let's suppose somebody shows up with the odd suggestion that 3x is a good linear approximation of 5x. Now I just want to, right off the bat, let's just laugh that out of the room. Come on, it's ridiculous. The linear approximation of 5x is 5x. Of course it is. It's already linear, right? It is its own best linear approximation. This is just, it's going the wrong way, right? This is not tracking the curve that it's supposed to be tracking. It's just no, right? Does that make sense? This is a bad linear approximation. And yet it has error approaching zero, and you can see the errors right here. Again, the difference between the value of the function and the value of the approximation. And that error approaches zero. So here's the problem then with this idea of, well, let's require error to go to zero. It doesn't eliminate this obviously bad choice. And so if you're going to impose a condition to try to describe, let's get precise and rigorous about what do we mean by a good linear approximation, it better eliminate the obvious bad choices. And this doesn't do it. Okay. So here's what we do. And again, I'm glossing over a week's worth of material in hopefully about 10 minutes here, right? So I'm not intending to hit all of the important ideas and full treatment, not at all. This is intended to be just a sort of a broad brushstroke. But we're going to look at this thing here called relative error. So relative error is not error. It's error sort of in comparison with how far away are you from the input. So it's the actual error, how far off is the output, divided by how far away is the input. That's that written here. Now, why would I look at relative error? It does what it's supposed to do. Here we go. Same example we looked at before. This function, like so, laughably bad candidate linear approximation there, 3x. We need some way of eliminating. We need some requirement that makes this fail. Again, error didn't do it. Error does not make this fail, but relative error does. Because here's your relative error. It's just, error divided by x, as it turns out. And that relative error ends up being, well, I'll do it like this, ends up being not zero. So if we make the requirement that relative error should go away, relative error should approach zero, but then good, as desired. It becomes clear that this is an unacceptable candidate to be called a linear approximation. It fails the requirement. This relative error does not approach zero. So now this is not enough justification to show why this is actually the correct condition, but I hope this at least makes it plausible of why we would be interested in vanishing relative error. It eliminates bad candidates, at least in this case here. And it turns out that this is exactly what we need, again, as it turns out. Now, here's what's in the book. The book says that a function is differentiable if this expression here approaches 0. And that's the correct definition. All good. Right? But it's pretty overwhelming at a glance, and you look at this and you're like, wait, why is there's 3 terms in the numerator? What's going on here? It's confusing, right? And what I like to point out is all this is vanishing relative error. Relative error going to 0. Don't forget, error is the difference between the real value and the approximated value. Don't forget that the approximated value is, and I am going to move parentheses around here over a little bit. You see how I have a minus sign thing. I'm going to put these parentheses like this. The minus sign then distributes into there and makes this a plus. Right? So that's just to be fair. And again, linear approximation is this right here. So this weird expression is nothing more than sort of a fully fleshed out formula for just relative error. And I just need that to go to 0. Okay, so again, a week's worth of material from Math219, and this is the 10 to 15 minute version that I think it makes the most sense in Math219. I want you to know where this expression comes from. It's this idea of vanishing relative error. But in fact, in this class, we're not really going to do anything with this as a definition other than look at it from a distance and hope we never have to ever actually do anything with it. All right, is that cool? All right. Okay, last thing, a little bit of terminology. If I sort of look at the terms a little bit differently in the numerator there, notice I can group them as that minus this. And that gives a different point of view than what we had been looking at, which was that minus this. And again, with the minus sign and the parentheses, y'all already remember that. So in this top point of view, we're looking at the actual value of the function minus the approximated value of the function. Grouping it differently like this, listen to how nicely this rolls off the tongue. The actual change in the value of the function minus the estimated change in the value of the function. So in both cases, whether you're looking at it that way or this way, in both cases we're talking about actual minus estimated. It's just that up here, it's actual minus estimated value of the function. Down here, it's actual minus estimated change in the value of the function. So anyway, it's the same thing basically, but just a conveniently nice different point of view. Terminology, the actual change in the value of the function is called the increment. We're going to use this word somewhat throughout the course. And the estimated change in the value of the function that we have right there, that's called the differential. And y'all might recall this from single variable calculus. They always talk about, dy, for example. They call that the differential. That's because dy is the linear estimate of the change in the value of the function. All right. And off we go. Here's the good news. Here's where all the ugly goes away. There's a closely related idea called continuous differentiability. It does some wonderful things for us. Here's the definition. A function is continuously differentiable If the partial derivatives exist and are continuous, it's as simple as that. This has always seemed wonderfully weird to me, because continuously differentiable sounds like it would be like an even more fussy term than just differentiable. After all, it's not only differentiable, it's continuously different. It seems like this definition ought to be harder to write down than the definition of differentiability. But it's not. It's super easy. You just look at the partial derivatives. Just make sure they exist. Make sure they're continuous. Game over. Super easy to confirm that a function is continuously differentiable. Yeah.
So how would the function that we were talking about earlier with the 1 and 0?
Yeah.
How would that not be continuous?
That's a great question. Let me point to, actually, I think I have a picture. Yeah, look at this. I copied my picture. Yeah, it's a great question. This is not continuously differentiable. As follows. When I am at the origin, the x partial exists because it's just 0 and I can just see it right there, right? But when I am just a skosh over, if I'm here, right, then the value of the function is 0 all the way along in there, then the value of the function is 1 up there, and then the value of the function is 0 again all the way along down here. So at this point, if I tried to compute the partial with respect to x, I'm dead in the water, because this function in that, on the blue here, it's not even continuous, right? There's this great big jump discontinuity right there. So partial derivatives don't even exist nearby. Does that make sense? Yeah, it's a great question, really good question, and kind of subtle to see how how it works out to fail. Yeah, everybody okay with that? All right. Okay. Yeah, so continuously differentiable, easy to write down, and furthermore, if that's the case, if a function is continuously differentiable, then we can immediately conclude that the function is differentiable, and we don't have to even touch all that business on the previous page about vanishing relative error and how would we confirm that it approaches 0. And by the way, one thing I swept under the rug there, to confirm that something approaches 0, you need to talk about multivariable limits. We kind of skipped that section in this class, right? And anyway, dealing with that definition is actually quite unwieldy. Here, we don't have to do anything of the sort. We can conclude differentiability just by making a couple of quickie observations. Here's that in action. Let's look at this function right here. Polynomial. Is that a differentiable function? Well, here's the thing. The partial derivatives are obviously all polynomials. Right? You take any polynomial, just think about how you compute partial derivatives. You're always going to get a polynomial. Here's the next thing. Polynomials are all continuous. That means that between the two of these facts, right, if you think about all together, if the partials are polynomials which are therefore continuous, that means the partials are continuous, which is what continuously differentiable means. And once you know that it's continuously differentiable, then it immediately follows that it's differentiable and game over. So, I mean, no discussion of vanishing relative error, no multivariable limits. It's just kind of a couple of key observations, and boom, we're done. Is everybody cool with that? Yeah.
What would be an example of
Yeah, it actually is kind of hard. I mean, I could give you some examples, but that's going to take us down a road that we don't need to go down. But there are some examples of functions that are differentiable, but not continuously differentiable. And yeah, it's a little bit of a digression to even write such a thing down. And that's part of why I'm comfortable skipping over all of this stuff, because it hardly ever comes up. right, in practice. If you're curious, come to my office hours. I'll be very happy to, show you some weirdo stuff. But it's in practice, it's not really, it doesn't come up that much. Okay. All right. Okay, here's another related fact, and this is just, while we're here, I don't want to prove this, but a neat fact to know is that differentiability implies continuity. I think that's probably kind of believable. Again, I don't want to get rigorous and prove it. Not what this class is about. But y'all remember a similar fact from single variable, perhaps. So I'm going to do what's called the contrapositive. I hope y'all are familiar with the contrapositive. If you're not, it's a good thing to look up. The idea is if P implies Q, then not Q implies not P. And if you just kind of think it through, it's a pretty easy pitch, I think. Anyway. So the contrapositive says if you have a function that's not continuous, then game over, it's definitely not differentiable. And here's how we can use this fact. If you look at this function that was our very first function to deal with in this weird area, and that function right there, it's pretty obviously discontinuous. Right? Great big jump discontinuity at the origin. If it's not continuous, then it follows that it is not differentiable. Yeah, so I don't have to worry about the rigorous definition of differentiability to decide this question. I can conclude that it's not differentiable just from its failure of continuity. Okay. All right. Okay, let's talk about derivatives. Y'all will recall that one of the first things I said about derivatives is there's a bunch of them. We've seen several of them at this point. Partial derivatives. Gradient vectors are kind of a derivative. The derivative matrix is a kind of a derivative in a way. And there's going to be another one that we're going to talk about pretty soon that I don't want to foreshadow too much. But anyway, several different kinds of derivatives. I want to try to persuade you now of which one is really the best one. And I'm going to do that by starting with this equation right here that we've talked about. This is our general formula for linear approximation. Notice this is in the vector-valued multivariable case, right? This is our most general kind of linear approximation formula. And now, real quick, remember, a linear approximation has several jobs. One of them, it has to agree with the function at the point where you're doing the linear approximation. That's one of the fundamental requirements. Right? So we can rewrite like this. Having done that, let me observe I can take this and whip it over to the other side of the equation. Just subtract it on over there. Okay. Now I want to look at this equation here. And what can I say about that equation? And let's look at the right-hand side. This factor here, x minus a, that's literally how much I'm changing the input to the function. From the point where I'm doing the linear approximation to the point where I'm evaluating the linear approximation. I was here, now I'm here. This is literally how much I moved in the domain. This is what we call the differential. I like to call it the input differential to emphasize this is the differential that's going in here. And then if you look at the right-hand side is how much did our linear approximation change? Literally, L of x minus L of a, that says the value of the linear approximation over here minus the value of the linear approximation over here. It's literally the output differential. Again, keep in mind, differentials are linear approximations of change. Right? So this equation tells us something pretty impressive about the DF matrix. The DF matrix is what you multiply by input differentials to get output differentials. Said differently, the DF matrix is what you multiply by input changes to get output changes. That's what derivatives do. That's the fundamental sort of unifying characteristic of all of our derivatives. Their relationship between input changes and output changes. And DF is the thing that does it in general, right? In this general multivariable vector valued case, the derivative matrix is the thing that does what derivatives are supposed to do. And just to, for sort of dramatic purposes, DF is the thing that turns input changes into output changes. Right, so you can see how it fits the verbiage of our previous sort of description. What do you think? Everybody on board? Now again, I made this comment a while ago when we were first starting off with derivatives that a lot of people like to hang their hat on the concept of a partial derivative. Partial derivatives, they're easy to compute. That's nice. Right? But they're kind of ridiculous if you think about it. I mean, how they apply in a real-world scenario. A partial derivative assumes that most of what's going on isn't changing at all. That's not that real world, right? Realistically, most things, most times you have a scenario, everything's changing, right? It's a fairly narrow hypothetical that only one variable would change. It's just not a very general concept. The derivative matrix as a whole, conveniently made up out of these super easy to compute partial derivatives. Yeah, fine. But the derivative matrix as a whole, that's the thing that always, no matter how many input variables are changing, will turn your whole input change into your whole output change. And I think that's a really nice, a really important observation to make about multivariable derivatives. Fundamentally, multivariable derivatives are matrices. Does everybody buy it? Yeah.
Is there any intuitive reason why the output differential should be the difference between the linear approximations rather than the functions themselves?
Yeah, that's right. Because what derivatives do is try to approximate things that we can't compute exactly, right? I mean, if we could compute the actual output change, we wouldn't need to approximate it, right? We would already have it, and this whole thing kind of becomes, unnecessary. Yeah, so the whole strategy of differentiation is to try to approximate something that we can't actually get our hands on by looking at it linearly. Yeah, right. All right. Okay, a little bit of terminology. Again, we've previously called this the derivative matrix. Now I'm going to just refer to it as the derivative. This is going to weird some people out because most people are accustomed to when you hear the derivative, you think of a number. Or maybe like a function. But if you think about it, a function is just a formula for a number, right? What kind of a critter is it? It's a derivatives in Calc 1 classes are numbers. Now a derivative is a matrix. And this is going to take some kind of mental adjustments, probably. So give yourself time to soak this point in. You should think of the derivative as being a matrix because input changes and output changes are vectors, right? So not really that surprising that the derivative, the thing that relates them, which should be a matrix. Okay. Also sometimes called the derivative transformation. After all, it's a linear transformation, whatever. Sometimes written as JF. That's a reference to something, a terminology called the Jacobian matrix. Kind of historical reasons. For whatever it's worth, I'm probably going to say Jacobian here or there because my mathematical upbringing involved this being referred to as the Jacobian matrix. So, whatever. All right. So, and you'll hear other people say that as well. Okay. Just to have a picture, keep in mind what a function does. A function takes an input point to an output point. So, for example, this input point right there goes to this output point right there, and the function f takes that input to that output. That's what functions do. What does a derivative do? A derivative takes not input points, but input changes and turns them into output changes. Linear estimates, of course, right? So derivatives take vectors then and turns them into vectors. So this is a nice way to think about it, I think, that again, you're a function point to point, a derivative vector to vector. Okay. All right, now a twist on this. If you think about it, you take the equation we've been talking about, just divide both sides by dt, and again, I don't want to get distracted by formalities. I'm just going to, quick and dirty, right? Just divide both sides by dt. And now, what is it that the derivative matrix is doing? Now the derivative matrix is turning a velocity. How fast, not how much, but how fast, what is my velocity in the domain, and turning that into output velocity. How fast, what is the velocity of the image in the target, right? But again, it remains that this is turning input vectors into output vectors, right? It's just that now I'm interpreting the vectors a little bit differently. This is no longer representing a displacement. Now this is representing a velocity, different interpretation of vectors, but the connection is still the same. How are we doing? Is everybody okay with that? Okay. Real quick, recall that in the case of real valued functions, the very first linear approximation that we wrote down for multivariable, right? It was the gradient, not the derivative matrix. So you can take all of the argument that we just made and just kind of go through it all again. It's all kind of the same, and you get to this conclusion that dot product with the gradient is the thing that turns input changes into output changes. And that's a perfectly reasonable point of view. Just keep in mind that that's really kind of what the derivative matrix kind of is in this real valued case. If f only has one component, if it's literally a real valued function, the derivative matrix only has one row. It's a row made up of all the partials of that function. The gradient is a vector made up of all of the partials of the function. They're all the same elements. They're just kind of arranged a little differently. The difference between the df row matrix and the gradient vector that you dot with is just kind of notation. Yeah.
So it's not, like that dx is not a singular variable. You're measuring the change amongst all variables.
Yeah, that's right, and thus the little arrow over the x. That's just to emphasize that that x is a vector, and the differential of the vector means change of the entire vector, which, as you say, is a vector of all the individual coordinate differentials. Yeah. Yeah.
Just notationally, is there a reason that there's no vector hat over the df?
That's a great question. In this case, it's because f is real valued, but you got me. Even in the vector valued case, I didn't put a vector over it, and not really. The vector hat is always kind of optional. I definitely do it here because if I didn't put a vector hat over the x, you'd think it was a coordinate, right? F, though, I've indicated elsewhere, is a vector valued function. And so I don't have to put the little vector arrow over it, and I don't know. It's kind of optional in some sense. There's a case to be made that for consistency, maybe I should. But you're going to see in lots of instances that people just won't. Yeah, right. Okay. All right, let's see here. So, okay. I'm going to draw the line right here. We're out of time. Y'all have a good rest of your day. See you on Friday. Yeah. Okay.